Hello, everyone. My name is Dimitri Racordon. It's very hard to pronounce if you're not a French speaker. It's OK. And I'm here today to talk about a very friendly programming language that's called Val. But before we start, allow me to give me a few words about myself. I'm a bit of an outsider in this crowd. I'm a researcher. I'm not a professional developer. And I'm definitely not a C++ expert. I might be able to write hello world, but that's about it. I love type theory and formal semantics. I write formulae with lots of Greek symbols for a living. So my view of programming languages and software engineering is a bit skewed by that background. But I also love systems programming, and I'm truly passionate about language design. So what I want to do with this talk is to walk you through the design of a new programming language that I think could be a companion for C++, or at the very least, a source of inspiration. To understand what Val is about, we first need to have a look at the concept of mutable value semantics, or MVS for short. If you saw Dave's talk on Wednesday, you already know what this is, but for a refresher, here's the gist. Mutable value semantics is all about local reasoning, which Peter O'Hearn described as follows. To understand how a program works, it should be possible for reasoning and specification to be confined to the cells that the program actually accesses. The value of any other cell will remain automatically unchanged. Put differently, you should never have to worry about an intended mutation caused by spooky action at a distance. And this is a very simple way to achieve that. In the strictest form, reference becomes second-class citizen. They can only be created implicitly at function boundaries, and they can't be stored in variables or object fields. So variables can never share a mutable state. That certainly looks like functional programming, right? But the difference with MVS is that MVS allows part-wise in-place mutation. One truly wonderful thing about C++ is that it's one of the rare contemporary programming languages that has first-class support for MVS. For example, in a program like this, modifying an element of v2 can happen in place without reassigning v2 to a whole new object. That is an in-place part-wise mutation. Further, because MVS upholds value independence, neither this mutation nor the next is shared. So if we output the size of v1, we can observe that it has not changed. We have local reasoning. So MVS is in contrast with reference semantics. It's a paradigm where you are allowed to observe shared mutation through aliasing. So in Python, for example, aggregates have reference semantics. So in Python, the mutation of v2 is shared, and that caused v1 to change too. So we lost local reasoning. And there is a myriad of problems related to reference semantics. In C++, they may cause undefined behavior, and in practically any programming language, they cause very hard to find logic errors. And Dave showed some of these errors on Wednesday, so please have a look at the video if you missed the talk. We also wrote a scientific paper on the subject. You can read it if you want to know more about the topic. Just skip the Greek letters when you get to the formal parts. I won't be mad. For the purpose of this talk, let's just agree that local reasoning is a very nice property, right? And we want to uphold it. So the basic idea behind Val is, can a language enforce the guarantees of MVS as practiced in C++ and without loss of efficiency? And I'm emphasizing here on this goal because our research started with Swift. And Swift has a pretty good support for mutable value semantics, but it relies on copy and write to mitigate the cost of copying. And don't get me wrong, Swift is quite fast. It's a fast language. But copy and write does incur a runtime cost, and it's not always easy to avoid that cost. So the question quickly became, what would Swift look like if it had only mutable value semantics? And we also wanted to explore support for non-copyable types, because Swift started with the idea that all types are copyable. And we wanted to look at what MVS can do for concurrency, because Swift adopted an actor model based on reference semantics. So eventually, the journey has brought us to a language that aims to address these challenges. First, Val should have a transparent model that users can rely on to get guaranteed optimizations and predict memory allocation costs. Second, users should be able to assume type safety, memory safety, and data risk freedom by default. Safety means that programs cannot have undefined behavior. That's actually not a very high bar. Most scripting languages are safe. That includes Python. But the difficulty is to avoid performance taxes at runtime while keeping the language expressive enough. And also, Val does not only care about safety, it also cares about correctness. That's why we're aiming for mutable value semantics. We want more than the Python-like safety. We want to help you reason about your code, about the correctness of your code. And we also want to make generic programming easy and reliable, so everyone can use it. It's not an expert thing. And finally, it's one of the reasons I'm here, we want to make Val interoperable with C++. So it's kind of a tall order. And before I show you some code, I'm sure you're itching to see Val code, let me acknowledge some of Val's biggest influences. First, if you know a bit of Swift, Val should look somewhat familiar. We borrowed a lot from Swift syntax and evolved or simply copied many of the features. Starting from an existing language gives you confidence in your design choices. It shows which features actually work for actual people and which require improvements because they don't fully address existing use cases. Of course, we also borrowed a lot from C++. And to its credit, C++ has two amazing features, MVS, as I already said, and generic programming. And with Val, we build on both of these concepts with the aim to make them safe and simpler to use. So we do not claim to have groundbreaking ideas, but our contribution is to offer a language that can express 99% of your regular code using safe constructs without loss of efficiency. For the 1% remaining, you can opt in on safe features to fill the gap. So put differently, most of the guarantees we get in C++ through good practices or code reviews are guaranteed by the compiler in Val. Don't be surprised if the way Val proves its memory or type safety reminds you of Rust. But we think our design is simpler and easier for the users. We focus on whole path relationships, and that lets us constrain lifetime naturally without the use of lifetime annotations and without fighting a borrow checker. In fact, one of my goals with this talk is to convince you that you don't even need pointers and references to write expressive and efficient code. I should also say that Val's goals significantly overlap with two other projects that I know, Carbon and the C++ core guidelines. But our approach is very different. We're offering safety by construction in a programming language that works the way your mental model does. Okay, now let's finally dig into Val. One thing that separates Val from Swift, C++, Rust, many other languages is that all copies in Val are explicit. And yes, even copies of integers. I know, this looks very scary, but bear with me. Before we came to this conclusion, we made a couple of observations that revealed, well, it's actually a good bet. To understand, let's talk about parameter passing conventions. Here we're looking at a Val function that takes an array of strings and prints the elements that it contains. The default parameter passing convention in Val is pass by value. So in the user model, x has an independent value in the context of print all. Pass by value gives us local reasoning. Nothing in the program can change the value of x on our feet. But some people might be worried that it could be costly to call print all. Especially if you have large arrays, it could be very expensive to copy those arrays, right? So for a C++ programmer, an obvious way to mitigate this cost is to pass things by constant reference. In a way, we have traded the safety pass by value offered for the efficiency of pass by reference. Yet, as Dave pointed on Wednesday, a C++ programmer will typically think of this parameter as though it had an independent value in the context of print all. And they will assume it will remain immutable. So the upshot is that passing arguments by constant reference in C++ is conventionally a way to achieve pass by value semantics, just efficiently. But what if we let compilers apply that optimization on their own, while preserving the guarantees of local reasoning? Well, with that in mind, we can now see that this copy is unnecessary. The compiler may just take a reference on fruits rather than a full copy, and the program will have the exact same meaning. In fact, Val compiler will even complain about that copy. What's interesting is that it shows most programming languages copy too eagerly. That includes C++. we don't need copies to implement pass by value. We can simply use pass by reference under the covers. Actually, we only need copies when we are forming new whole part relationships or when we are returning values from functions. When that happens, we say that values escape. But even when a value escapes, there may be no need to copy it. Here we're looking at a function that returns a number of elements that can be appended to an array before new memory must be allocated. Since space is escaping, I put an explicit copy, right? This is what the rule says. But the compiler suggests that I remove the copy. Well, the reason is that the return statement is the last use of space. No other code is using that value anymore, so we may as well let it escape right here. So as you can see, as the copies must be explicit in Val, in fact, we don't have to write many of them. Obviously, pass by value is not a one-size-fits-all solution. So Val offers other parameter passing conventions to express different intentions at function boundaries. These passing conventions are at the core of Val. They let us safely express 99% of the low-level bit pushing you can do in C++. So let's illustrate with a running example. Here we're looking at a declaration that introduces a type, vec2. It's defined as a pair of floating point numbers. Let's also make this type copyable. For you C++ people, this is not subclassing. It's declaring conformance to the copyable concept. That will give us a copy method and help the compiler come up with suggestions when I forget explicit copies. And now let's define a function that offsets a vector by a given amount on both of its components. With pass by value, such a function could be defined like this. The parameters of offset use the default convention, which is called let. And it denotes pass by value. Because it's a default, no annotation is needed, but we can make it explicit if we want. Let parameters can be understood as pass by constant reference from a C++ perspective, but with the additional guarantee that arguments can't change in any way during the call, right? We preserve local reasoning. So if you saw Dave's talk on Wednesday, let parameters are the same as his in parameters, the one he proposed for C++. So since V and D, the parameters are immutable, we can't write this alternative implementation. It would violate the guarantees Val gives to the caller. But fortunately, the compiler can come up with a solution. It's offering to copy the parameter to a local variable. By the way, note here that the ampersand is not the address of operator from C++. In Val, in-place mutation is signaled with a marker at the start of the mutated expression. It's something we took from Swift. So notice there is a fix button. The idea is that we could have IDE integration with Val, and if we click that button, the compiler can make the change on its own. We can do that, something Swift does for other kind of fixed suggestions. So what happens if I click on the button? Well, here's what we get. We create an independent value and initialize a temporary local variable. Now the mutations occur at the temporary, leaving the argument intact. Note that C++ would have made you pay for the copy to uphold the independence, but just to call the function. In Val, the copy is delayed until you actually need the copy. Also, thanks to value semantics, it's fairly easy for the compiler to determine whether a mutation is meaningful. Should we remove the call to print, the compiler would complain that the assignment is useless. If we were able to determine that there is no side effect, we could even remove the call altogether, but that's a bit more difficult to do. We would have to think in terms of purity, which is harder. The next convention is in-out. It signals mutation, and it's exactly as Dave showed on Wednesday. Conceptually, in-out parameters can be thought of going into the callee when the call starts and getting out when it returns. At the implementation level, though, we don't need to move or copy anything. Again, we can just use references under the covers. So from a C++ perspective, in-out parameters can be understood as pass by mutable reference with a couple of extra guarantees. In-out parameters values are mutable and unique. By unique, I mean that the parameter is the only means of access to the storage, mutably or otherwise, for the entire duration of the call. Guarantees of independence are how Val ensures safety without loss of efficiency. And it's also how Val helps you write code that makes sense. To illustrate, let's look at this C++ example. Because the parameters V and D may overlap here, the callee cannot assume that D won't change when it modifies V. And that can lead to surprising results. The issue here is that functions do not compose well with reference semantics. In contrast, that situation cannot occur in Val. The compiler detects that we're attempting to create two overlapping accesses, one of which being mutable, and so it rejects our program. As the compiler suggests, the fix is to copy vec before the access starts, so that we can call the function with two independent values. So here's the fixed program. Now we have this underscore vec, independent value, and we don't break local reasoning anymore. A third passing convention is called sync. Sync parameters consume the arguments. They go into the callee and never come back. So from a C++ perspective, they can be understood as being passed by value with a force move at a call site. Unlike in C++, though, we consume the argument, which means that the move is destructive. In fact, in Val, all moves are destructive. So attempting to access a value after it's been passed to a sync parameter is an error. That's called at compile time. Again, the fix is to copy vec so that we can work with two independent values. I'm sure you're getting a theme here. Another important thing to note is that because moves are destructive, Val does not make any guarantee as to when exactly the destructor of a local object is called. I'm sure you're starting to get worried, but you can have your user-defined constructors. They will be called when the object dies. The language doesn't guarantee anything more precise than that. In particular, it doesn't promise anything about the order in which destructors are called. So lexical scopes are irrelevant when it comes to destructors. So what happens to RAII? Well, you don't have it in Val, because there are better ways to guarantee the execution of some arbitrary code at the exit of a scope. You don't need to hack object destructors to do that. What do we do in Val? Well, we have defer blocks that are guaranteed to be executed on all exit paths from a scope. So if we had to close sockets or deallocate unmanaged memory in some specific order, we could just use one of these blocks. We would not have to hack an object to do that for us. Now, you may have noticed that the call to offset sync here looks a lot like a functional update, which is a typical way to achieve mutation in a functional programming language. In fact, the correspondence between in-place mutation and functional updates is very real, and it can be used for the sake of performance. Let's dig into this observation forward. Arguments to sync parameters are known to be unique, right? We consume the argument, it was unique. So another way to implement offset sync is to modify the argument in place. And we may also implement offsetting out using a functional update, because a callee is entitled to do anything with its value, in another value, including destroy the value and put one back before it returns. But how is that useful? Well, let's look at a more complex example. Some code, but don't worry, we'll go through it. Here, we're defining a type to represent polygons with arrays of vertices. We're also defining offset functions for this type, similar to the offset functions we had for vec2. So this one takes a polygon by value, and it returns a new one. This one takes a polygon and mutates it in place. And this one takes a polygon, consumes a polygon, and returns a new one, presumably reusing the storage of the polygon it consumes. But now copying polygons can be expensive compared to very cheap vectors, right? Because we have arrays, we could have a lot of vertices, very expensive to copy a polygon. So choosing the right offset implementation becomes important. For instance, this call here causes a wasteful allocation. Remember, let parameters behave very much like constant references. So passing shape that way implies that offset polygon must allocate a new object at some point. When it returns, we'll have two distinct polygons in memory, while we could have just reused the shape storage. So that's the cost of a functional update here. There are ways to remove that cost, but you need a very clever optimizer, and it's not always easy to do that. In Val, we could use offsetting out to manually make the update more efficient. But having three different versions of this offset function is poor ergonomics. The user has these three things that are named almost the same, and they don't know which one they should choose. They need to read the documentation for all three in detail to make sure they understand all the differences, and only then they can choose the right one for their use case. It's cumbersome. So wouldn't it be better if we could just express things more naturally? Maybe you would like to have a do the right thing variant that does what that just chooses the best implementation looking at the user's code. Well, it turns out we can do that. Instead of overloading and naming conventions, Val proposes to group method implementations in what we call bundles. Now, there's only one declaration for all of these variants, with only one signature and one documented meaning. The bundle also teaches the compiler about the relationship between these different entities. So now the compiler can select the most appropriate candidate depending on how it is used. So let's look at the call again. What implementation should Val choose? Well, we just want to change the value of shape. We don't want a new value, so the compiler can use the inner variant here. What about this function call? Well, now we want to hold on to the shape that we have, because we will print it later, but we want to print the offset version. So here the compiler will choose the let variant. And what if we remove the last print statement? Well, now we don't need the value anymore. So we might as well consume it here, and the compiler can choose the sing variant. The takeaway is that bundles let you write code in a very natural way, and Val will choose the most efficient implementation on its own. Now let's go back to the relationship between function updates and in-place updates. We said there is a way to synthesize the sing version from the inode one and vice versa. So if we can't do better than a synthesized implementation manually, that means we can omit the inode variants and let the compiler implement it for us. The compiler can also implement the sing version from the let one. So again, if we don't have a way to write a better version, we can also remove it. What's left is a model with 3 implementations of offset, but 2 of which have been synthesized. So you don't need to duplicate code to use that feature. For completeness, there is a last convention, passing convention, that's called set. It's rarely used. It safely takes an uninitialized parameter and makes sure it gets initialized before it's ever used. Just know that it exists. For now, we don't need to get into more details. It will be relevant later. OK, now that we are clear on passing conventions, let's talk about local bindings for a minute. There is one important observation at the heart of Val, is that a let binding is kind of the same as a let parameter in a function. To understand what I mean, let's have a look at this program. X is bound to the first component of velocity. But notice we're not copying anything. Remember, all copies are explicit, even for floating point numbers. We're also not moving anything. If we did, the last call to print would have been caught as an error. Instead, we're creating a temporary access to a part of vector that is bound immutably. Bound immutably means that swapping these 2 lines will cause an error, because now there is an overlapping access on velocity. Note that the compiler suggestion is to copy the value under mutation rather than moving the mutation someplace else. That's because the compiler can't guess whether the mutation must occur before or after we print. Instead, it's operating as though the user is dealing with independent values, and every time they perform a mutation, it suggests copies where a language such as C++, Swift, or Rust would have made one. By the way, if you're a Rust enthusiast, you may think that this whole stuff is just borrowing, right? The Rust compiler would also reject the program. It would complain that the first component of velocity is being borrowed immutably. But if we keep references out of the picture, we can just think in terms of useful lifetimes and reason locally, without the need for reference semantics. The useful lifetime of binding starts with its initialization and ends with its last use. Here, that means the useful lifetime of X covers this section of the program. It starts here, when X is bound to the first component of vector, and it ends here, because the sprint call is the last use of X. So if we move the mutation out of the access lifetime, the program is legal. Of course, the same reasoning applies for local in-out bindings. Here, we're creating a temporary mutable access to velocity's first component. And because that access requires uniqueness, attempting to read the component's value via another access is caught as an error. We can apply the same kind of reasoning that we learned with the parameter passing conventions. And what about var bindings, which is the last kind of binding that we have? Well, var bindings do not create access to an existing object. they represent access to an independent value. So in a way, they relate to the sync passing convention. That means initializing a var with a part of another object consumes that part. As a result, velocity is no longer alive by the time the program calls the first print, which is caught as an error here. Another central feature of Val is the ability to temporarily project views of an object. That feature comes from Swift. It's completely brilliant, and we're just improving it in Val. So we already seen how to create let or in-out bindings to stored parts. But what if we want to project a view that isn't anywhere in memory? Well, for that, we have first-class computed properties. Here we're looking at a property declaration that projects the value of an angle in degrees, although it is stored in the type in radians. Here, in-out is signaling that the accessor is mutable. And so we are allowed to bind that property mutably. Here's how that looks at the call site. There's no need for any kind of ceremony. We can create an in-out binding to get a mutable view of our angle in radians, although that property doesn't really exist. It's been computed. Projections work by inverting control between caller and callee. When degrees is accessed, the control is referred to the callee, just like in a regular function call. The body of the accessor is executed through the yield statement to prepare the value to project. Then control is transferred back to the caller, which can use the projected value. After the projection's last use, so at the end of the useful lifetime, control is transferred back to the callee. And we can use that as an opportunity to write back the mutation made to the projected value to the owning type. So finally, control goes back to the caller, and the property access ends. Simple, right? And we can do even more with projections. If a projection has one or more parameters, it's called a subscript. So let's illustrate with a slightly more example. Here we're looking at a type describing a 2x2 matrix of floating point numbers with a column major representation. This representation gives us a simple way to access an entire column. But we also want access to the row, so we're defining a subscript to access an entire row using its index. In other words, we want to be able to view the matrix as though it had a row major representation. Properties and subscripts can define mutable accessors. Just like with method bundles, the compiler selects the most appropriate one based on the caller's context. So a let accessor creates an immutable protection, and it's used when the compiler detects that the subscript or property is being accessed for reading. Here, how we look at the call site. An in-out accessor creates a mutable protection, and it's used when the compiler detects that the subscript is accessed for both reading and writing. If you only want to write your property but not read its contents, then you can use a set accessor. And finally, we have a sync accessor that consumes the object and produces a new independent value. It can be used to extract a projection from an object that reached the end of its lifetime. So for instance, let's say we want to get a row, we don't need the matrix anymore, then we could extract a row from the matrix and then get rid of the matrix. There's much more I could say about subscript in Val and projected values. We can do amazing things, complex things to represent slices, for instance, but there are other things I want to talk about, so let's move on to another topic. You can ask me questions if you want afterwards. All right, unsafe operations. There are operations that do not fit the safe subset of Val. For instance, you may want to manipulate row pointers to interact with a legacy library that you have. Or maybe you want to perform unsafe memory operations for the sake of performance. In those cases, you can opt into an unsafe feature. So let's study an example to see how that looks. All right, this is a lot of code, but don't worry, we'll walk through it. We're looking at the declaration of a type representing sequences of bytes. And I'd like to apply the small object optimization. So this type contains a variant with two cases. The first is a buffer of 7 bytes, and the second is a pointer to a heap allocated buffer. So the idea is that I can use the inline buffer to store up to 7 bytes, and if I need to store a larger sequence, then I can point to an out-of-line buffer. Incidentally, the size of contents here is exactly 1 word on most platforms. And you can ask me later if you want to know how that works. Let's have a look at the initializer of the type now. First, we're looking at the size of the array that we got as an argument. If the array has 7 or less elements, then we can initialize the small buffer, and we're happy with ourselves. Otherwise, we can allocate a buffer dynamically and use unsafe operations to initialize its contents. So here we're performing pointer arithmetic to get the nth element of the buffer, and here we're using the result of that computation to initialize storage. Notice that the entire expression is marked by this unsafe marker. It simply signals to the programmer that the expression uses unsafe operations. Both methods, advanced by and initialize to, could cause undefined behavior if we use them incorrectly. So the marker says that we need to vet this line extra carefully during code review. Assuming that we do that vetting carefully, the expression is safe in the same sense that Haskell is safe because we trust developers to have done the hard work. Now let's look at a subscript that gives us access to the contents of the type. First, we're making sure that the index is in bounds, and we terminate the program with an error message otherwise. Remember, Dave told us on Wednesday that termination is a total legit way to uphold safety. Then we're searching over the actual value of the variant. In the first case, we can simply index into the fixed size buffer. That operation is safe because a fixed size buffer implements its own bounds checking. And at that point, if you're worried about redundant checks, remember that the compiler has independence guarantees, and so that allows it to remove the redundant checks reliably. In the second case, however, we must use an unsafe operation again to dereference the nth element of the heap allocated buffer. Now, it's important to realize that while our type uses unsafe operations internally, it only exposes a safe API. We, the developers, we made sure that there is no way our implementation can cause undefined behavior, so all is well. And because safety composes, we can fearlessly use this type without threatening the safety of the program. So you can just plug this type in the safe subset of Val, and everything is safe. Now let's turn to generic programming, which is another big goal of Val. The story for generics in Val looks pretty much like what Alex Stepanov envisioned 20 years ago. And I really recommend everyone to watch this wonderful talk. It's an Adobe seminar from January 2002, where Alex explains its vision. In a nutshell, concepts, like we have them in C++, are just like Java interfaces with types and values. And generics are type checked separately, which is different than concepts in C++, of course. And that's really key to develop generic algorithms that don't break when you instantiate them. I show an example. Generics can be dispatched statically, but Alex also explains how concepts could be used for dynamic dispatch, which has its use case. Again, I will show some examples. At that point, we should know that Alex's vision is no longer rocket science. Many languages have implemented those ideas that include Swift, Rust, Scala, Haskell, and I'm sure many other languages. So we just need to get on board. But how does it look like? Well, let's start simple. In Val, types, functions, subscripts, they can all be parameterized by generic arguments. There's nothing groundbreaking here. We're declaring a generic function that counts the occurrences of a specific element in any kind of collection. So we're using the familiar angle brackets to define a generic type parameter representing the type of the collection to inspect. And this parameter is bound by a collection concept, which is what we call a trait in Val. And it describes the API of what a collection should be. We use that API to implement the body of the function. Here, for example, we rely on this reduce method, which is defined by the collection concept. Just like in C++, arguments to generic parameters can be inferred, and the compiler instantiates the function for the type of fruits. Now, a very important difference between Val and C++ is that Val does type checking at declaration rather than use site. Here that means that we know for a fact that reduce is a method of items because we said that its type conforms to collection. And because that API is properly checked, an IDE can provide code completion, show me the method's documentation, let me jump to definition, etc. So we can really improve on the user experience. That's not realistically possible in C++ because concepts are defined in terms of predicate expressions rather than interfaces, and also because overloading gets in the way. We also know that the equality operator is defined for the elements of items because we said that the type must conform to a quotable. In fact, if I remove that constraint, Now the type checker will complain with a very clear diagnostic reported directly inside the method and showing us that we didn't state some of our assumptions. There is something wrong here with this algorithm, and I don't need to instantiate it to get that message. Note that we also get good error diagnostics at the use site if we're not using the API properly. Okay, let's contrast that with the user experience we get in C++. Here's a transliteration of the Val program that we had before. At least I tried to make one. Tell me if it's wrong. And first we can see it's a little denser, but I think it looks reasonably similar. So what happens if we call occurrences, this function, with improper arguments? Well, because we used concept, we did the right thing, we get a relatively good diagnostic, telling us that the argument doesn't satisfy the stated constraint. So this seems perfectly all right. But what happens if we remove the equality requirements? Well, now I get a wall of error, and the first diagnostic is reported here in the function. And I think that's quite confusing for the end user, especially for shipping that function in a library, because it doesn't properly show that they didn't use our API incorrectly. It looks like an error deep in a library that are just imported. It's weird. But is that really such a big deal? At the end of the day, the type checker did reject our program, so everything is right. Well, the issue is that nothing compels us to fully specify the API of a function, whether we use concepts or not. We can always forget our requirements, and the compiler will silently accept our code. So without that main function, our code compiles just fine, and that's very dangerous. In fact, Alex pointed exactly to this problem 20 years ago in this talk. Think about it. We could ship bugs that go undetected for years until a function finally gets called with a type that doesn't satisfy the unspecified requirements that we didn't think to put there. And yeah, can I take the question at the end? Yeah, thank you. And it's not so unlikely, because it's hard to get a sense of the full API that a bunch of concepts describe. It's also hard to get a sense of the complete assumptions that are made by a complex function. I think we need compiler support. At least I do. So how do we define concepts in Val? We can use traits. A trait is a set of method and property requirements along with associated types and values. Here we're saying that a collection is a type that has two associated types, requires 3 methods to handle its indices, and 1 subscript to access its elements. Note that collections in Val use indices rather than iterators, because iterators have reference semantics. A trait may also define requirements that have a default implementation that you can override in the conforming types. Traits can refine other traits by adding new requirements. Here, for example, we're defining traits that describe bidirectional collections as type that not only conform to collection, but also define a method to produce the position before some other position. That's how we go backwards. Unlike C++, Val requires conformance to a trait to be declared explicitly. That conformance is type-checked at the point of declaration, so there is no way we could accidentally forget one requirement. Again, it also means that IDE can provide stops for the requirement that we forgot to implement. This is something Java developers do in Eclipse when they implement an interface. Conformance can be declared in the primary type declaration or with a conformance declaration. You can ignore the details of the body. The point is that you can specify how to implement requirements retroactively. This feature is useful not only to organize code, maybe I want to separate my conformances in different files, but also to add post hoc conformance to types that might be defined someplace else, maybe even in an imported library. And finally, we may also confine conformance to a specific trait inside the scope. Here, for example, we know giving something mutable roles is generally not a good idea, so it might be why we want to scope the conformance of vec2 to collection just to that scope, because we need to perform some specific operation in that scope. Now, the conformance of vec2 to collection is confined, and attempting to use vec2 as a collection outside of this full namespace will result in an error. Using traits, we can do a lot of generic programming without ever typing an angle bracket, in fact. So here we're declaring a trait extension that allows you to add method to a trait. And we're declaring a method reverse for all types that conform to collection. Again, you can ignore the details of the implementation, just focus on the declaration. Notice that the extension is conditional. It applies only to types whose element associated type is copyable. So we can initialize this array by copying the elements of self. Reverse looks like a regular method, but it's generic over any collection whose elements are copyable. And because it's a method, we can call it with the standard method syntax. So we get a very natural way to introduce and use generic algorithms. Extensions can also serve as customization points. To illustrate, let's change the return type of reverse first. This type might be a bit complex, but it represents an opaque type. It's a way to hide information from the API of a function and let it pick the return type it actually wants. So the only thing we know from the outside is that the function returns some collection type that stores elements of the same kind. While we are hiding the type information to the user or to the type system, the compiler knows better. The compiler knows the actual underlying return type, just like a C++ compiler knows the actual type of a lambda. So that means we don't have to pay any dynamic dispatch tax when we call isEmpty here, because we know the actual type. The compiler knows. But what does this information hiding can do for us? Well, if we hide the specific return type of a function, then different implementations can choose different return types. And we can exploit that for specialization. Here, for example, we are specializing the reverse method for vec2 so that it simply returns another vector rather than allocating a brand new dynamic array. There is much more I could say about specialization and customization points, but I think we don't have time to delve further into details, so instead, there is one last feature I'd like to show in the context of generic programming, and that is type erasure. Val has a built-in support for type erasure with a feature known in the literature as existential types. So Klaus, who's here, gave us a great talk about type erasure, and I highly recommend you watch it if you missed it on Wednesday. And I will shamelessly reuse his example to show how Val works. So let's say we have different shapes represented by these simple types. We have a circle, a rectangle, and now let's define a trait that describes things that can be drawn onto some Canva. Remember, conformance can be declared retroactively in Val. So these drawable traits doesn't have to intrude on the shape declaration. I can just describe how those things can be drawn after the fact. But now let's say we want to create an array of drawable things. Well, the issue is that arrays are homogeneous collections, and we don't have a base class for all our shapes. In fact, Val doesn't have base classes at all. If you want to know why, then you can watch this great talk from Sean Parent. So we could go ahead and use the technique that we were taught on Wednesday to implement a type erase container for drawable things. This is what it looks like in C++, or at least my take on it. The whole thing is about 30, 40 lines of code. It's solid, beautiful, efficient C++, almost fits in a slide, has value semantics. It's absolutely wonderful. But you know, it's work, and we have to do that work every time we want the type erase container. So yeah, there are trade-offs. The good news is that Val can do this work for us. So in Val, this type is called an existential type, and it represents a container for things that satisfy some API. Here we know that the content thing is an object whose type conforms to the drawable trait. And using existential type, we can now declare an array of drawable things and fill it with all sorts of shape without any ceremony. There is no pointer, no base class, everything is safe. And what can we do with this array? Well, because we know that drawable things can be drawn, as the name suggests, we can write a function that draws every shape in a collection. In each loop iteration, we don't know the actual type of S, but we know that it's a drawable thing. It satisfies the trait. So the compiler knows that the method call here is legal. And at runtime, the program will use dynamic dispatch to execute the method corresponding to the object stored in the existential container. So I think this is pretty cool. But we can do even more sophisticated things. Remember, traits can have associated types and values. And it's harder to write existential containers for these kind of traits because there are parts of the interface that might not be concrete enough. What do I mean by that? Well, let's see what Val has in store. Here we're declaring that fruits is a collection, but it's not just any kind of collection. It's one whose elements are strings. So we can access the parts of collections API that are fully specified, knowing that its associated type is string. For instance, we can get the collection's first element because we know that it has to be a string. And the compiler can apply static dispatch here because the type of f is known at compile time. The collection has an existential type, but its elements have a concrete type defined by its API. What we can't do is make assumptions about the parts of the API that we don't know. Here, for example, we don't know whether the index type of fruits is an integer. At least we don't know at compile time. So that's not part of the existentials API. So trying to index a collection with an integer is an error code at compile time. We don't have enough information here. Okay, let's talk about concurrency for just a while. While we still have to investigate on efficient implementation strategies, we already identified some of the core principles that will pair well with value semantics. Spoiler alert, can express the same things as senders, receivers. In Val, we use spawn to evaluate arbitrary code asynchronously. Here's just an expression, and here's a couple of statements. Those spawn expressions then can be joined when you actually need the result of something. A very important feature of that model is that it avoids the so-called function coloring problem. So functions may spawn computations anywhere. Any function can spawn a computation. There are no spawning functions and non-spawning functions. This is a design choice, and it has consequences. At least it has consequences on the implementation. For our case, for now, we're leaning toward a stackful model, which would support this kind of thing, and perhaps you could switch to a stackless model when the optimizer can determine stack requirements. But again, as I said, we need to investigate on these things. Because of the asynchronicity of spawn, this program here breaks the law of exclusivity, the fact that we can't have different concurrent mutable accesses to the same thing. So here the compiler complains that we're creating overlapping accesses on work list. This is a very similar example as the one we showed with the local in-out bindings, right? So this seems like a limitation. How can we parallelize work with this system? Well, what we can do is have library provide operations to simultaneously expose non-overlapping slices of a single container for mutation. And so here we could, for instance, use that to create two non-overlapping slices of our task and then run things in parallel. In the introduction, I said that I would talk about the difference between Val and Carbon. So Carbon is a project initiated by Google to develop a successor for C++. I'm sure you've heard about it by now. And it has very similar goals as Val. It aims to be fast, safe, simple, and seamlessly interoperable with C++. But for the sake of time, let's focus on the differences. And the most significant difference between the two projects is their approaches to memory safety. Val is safe by default. We may opt in unsafe features, but otherwise, all constructs are guaranteed to be safe. That includes memory safety, type safety, and freedom from data risk. In contrast, Carbon plans on developing a straightforward path for migrating from C++ first, and incrementally improving on safety later. So in a way, Carbon is unsafe by default, like C++, but you can opt in safety using compile time or runtime checks. And I would call that a post-hoc approach to safety. A post-hoc approach like that has obvious advantages. It shows a simpler and faster path to evolution. Most of the C++ idioms, which we've come to enjoy, can stay. That's a pretty nice deal, and at the very least for the short term. And if Carbon succeeds, you will be able to adapt it and make your code base safer with very little refactoring. But in the long term, I personally believe that safe by construction is a better bet. There aren't any tricky cases that a static analysis might fail to handle, or runtime checks that might be missed during testing. Safety by construction gives provable guarantees that can make their way into a specification without any asterisks. So I firmly believe that safe is better than safer. A safe by default language actually lifts the burden of making sure that your program doesn't suffer from undefined behavior. A safer language only promises it's less likely to cause undefined behavior. Okay, the question then, an obvious question is, can't we just get from safer to safe? Just a matter of time, right? Well, maybe we can, but sound approaches to good old C++ are pretty difficult to design. In fact, there is a large body of research. Remember, I said I'm a researcher, and we really tried. And as far as I know, sound approaches always rely on Rust-like annotation system, or they impose heavy restriction on mutation. And I believe this is a symptom of relying on pointers and references to express mutation. In fact, I'll be a bit bold, and I bet that if we do get to safe, then we'll just reinvent Val. But we will have an inferior user experience because we will have started with pointers and references instead of value semantics. So we'll have a language that doesn't fit the way you think about your code. I should also say some more about another project I mentioned in the introduction, which aims to define a set of core guidelines to help C++ programmers write simpler, more efficient, and more maintainable code. These guidelines effectively describe a subset of C++, which static analysis is expected to be able to identify most common memory errors. The advantage here is that you don't even have to learn a different programming language. You write modern C++ and you get safety for free. We don't have time to get into the details, but there are very, very good ideas in this project, and I really like them. I think we will probably reuse some of the defaults for the C++ Val interp. But again, it's a premise for a safer experience, not a safe one. Of course, there is no free lunch. Surely, losing the ability to directly access data through references or pointers, it changes the way programs are written. It's different. But in exchange, we get local reasoning and guaranteed performance. So I'd argue that these limitations are actually a win. They make programs simpler to understand for both humans and machines. Your compiler can optimize your code better if you have value semantics. And if you really need it, you can always opt in an unsafe feature and prove safety on your own with careful programming, runtime checks, or maybe you can even use a static analyzer. And you can build safe components. We did one. And these safe components can naturally blend in the safe subset of your language. And if you need to remember only one thing, that's the takeaway I'd like people to think about: safety by construction. Anyway, that's it for me. Thank you very much for your attention. Catch me if you have questions. Please visit our website, val-lang.dev, and reach out if you want to get involved in any way, shape, or form. Thank you very much.
Thanks a lot for your talk. The main question that I had throughout the talk is, in particular, in comparison with Rust. To me, it seems a bit like Val, or the approach that Val takes, is kind of fixing a subset of the safe pointer features that Rust has. Like, for example, lifetimes, just enforcing a specific model on them, and then you don't have to specify them. And like removing some features, like having multiple read references is not possible if I understand it correctly. You just have one in-out, for example, or you have one let, and you can't have a second one to the same variable, right? So this, like the question is, doesn't this in the end result in more code that needs unsafe features where all bets are off? So did you actually compare which parts of the libraries you can write in Rust safely versus write in Val safely?
Okay, that's a pretty good and fair question. In fact, we can do almost anything that Rust can do in the safe subset of Rust. It's just that we are not calling these things references. You can have multiple let bindings if you want, just as you can have multiple immutable borrows in Rust. And you can have only one in-out binding, just you can have only one mutable borrow in Rust. And so very similar things. We're just not using references and pointers in the user model because we believe it's simpler if you move them out of the picture. That now you don't need to have the lifetime annotations and all this stuff. Now there is some of the things that you can do with lifetime annotations that we can't do in Val. It's kind of very technical, and I don't think I have time to show that just in a Q&A, but come later if you want to have examples. There are not very common use cases, and I think we can safely assume that there is a simpler way to express them in Val in 99% of the cases. It's a claim, and it has to be tested. Rust is an existing language that runs in production, and Val is a research project that doesn't have a finished compiler yet. So, of course, I'm just assuming and projecting, but yeah, the languages are very similar. It just have a different model for what the user has to think about.
Thanks.
We have questions from online. How does the compiler choose the correct passing convention if it's not clear whether the original variable is used after, such as due to conditionals?
Such as due to?
Conditionals.
Well, the compiler uses a conservative approach. So if there might be a chance that there is a use after a specific call, then it's not the last use, right? The last use is the last provable use of something. It's just very conservative approach.
You mentioned that you have projections, and then there's also synthesis for method bundles. Do projections also support synthesis?
Yes.
Okay.
Yes.
Could they usually be synthesized from just one, or do you find that you have to do maybe two?
Yeah, but you need the in-out version, because if you want to have mutation, then you need to have an in-out projection.
That makes sense. Projections feel like they're meant to be used in an in-out fashion.
Yeah, they could be used just for reading, but if you want mutation, then you need in-out.
Another online question. Is defer really better than Rye? A couple disadvantages I can think of are that a dev might forget to write the defer, or that the dev might have to repeat defer code in multiple places.
Yeah, that's true. That's one trade-off. But if you think about it, there are many use of RAII objects that you can also just forget to use that specific object, because that specific object you use not for the resource itself, but to encode some specific thing that you hacked, basically, to get your RAII. As I said, you can have user-defined destructors. If you want to manage a pointer yourself, then you can do it. Or the bytes type that I showed could have its destructor. The idea is that if you need to manage resources, you can do that as destructor. What we can't have is, what we don't need, which is better expressed with the defer blocks, is specifying the order in which things are expressed.
Hi, thanks for the talk. Can you, probably this is multiple talks, if I don't know how many, but can you expand on C++ interoperability? Like, I don't know, the worst thing comes to my mind is exception propagation and stuff like that. What's your plans on supporting such features of C++ in Val?
Well, I can't answer for exceptions. I'm not an expert in C++, so I don't know all the details of what would have to be taken care of, and this is something we didn't have explored in details yet. I'm sorry, I can't give you a better answer.
Another online question. How stable is the language, and where do you need help?
Oh, interesting. Well, this is very early work. I didn't have a status slide. Basically, we are still, well, I'm still writing the compiler. We have a specification. Most of the type system and the semantics of the language have been specified. It's not formal, or my bar for formal is pretty high. Remember, I write Greek letters for a living. But yeah, we have the semantics figured out. Of course, some things might still change, but this is pretty solid already. And yeah, we need help evaluating the language. People can write code if they want in the compiler. Feel free to submit pull requests or reach out. And yeah, just get feedbacks. Feedbacks are good. All right, that's it. And we passed time, so thank you very much again, everyone.